Okay, so to sum up what I was just saying, basically, if we want to compute the expectation of y given x, okay, and then we have, let's say, we assume that we have the CDF in which we have beta hat node plus beta hat 1 x1 plus, we can have more than 3x's, but just let's take an example of 3x's. And if I'm asking you about the impact or the effect of this specific variable, which is x1, then I have to tell you something about x2 and x3. One option is either I'm going to tell you to set x2 and x3 at the means, or I'm going to give you given values for x2 and x3. Okay, so x2 and x3, if I'm not concerned about if I'm holding them constant, then I have to know holding them constant at which value. Is it a mean, or I'm giving you specific values? Okay, the example that you had in the fall of 2016, I'm asking you to do it at the means. So I'm giving you the means, the averages of x2 and x3 and x1. Okay, so I'm giving you the averages of all these, and this one would increase 1 unit from its average. Okay, and these are set constant to their average. In the example that you have in your textbook, you're given values. Okay, they have a given values for these coefficients. I'm sorry, for these variables. I'm going to show it to you. I want you to, whatever I'm saying about the CDF, just apply the same for the logistic distribution function. So I have the same thing. It's either I'm going to ask you at the means, or I'm giving you specific values. So the example I want you to see, I want you, of course, to answer question 1 of the fall 2016. It's very, very, very important. And I will ask Raimondo to do it with you next week in the recitation. But before you go to the recitation, be prepared and just answer the questions. So in case you have some clarifications, you have the time to ask instead of going through the question from the beginning. Okay? All right, so the other one, which is the one from the textbook, it's actually from page 594, 595. Okay, and this example is measuring the labor force participation rate for females. So the example in your textbook, of page, actually it starts at page 593, not 594. So 593 to 595. Okay, it's actually measuring the labor force participation rate for females as a function of a group of variables. And this is a binary dependent variable. So it's going to be, this variable is going to take 1 if the woman is in labor force, and it's going to take 0 if this woman is not in the labor force. Okay, so it's a binary dependent variable, and it's a function of, as you can see it in your textbook, is a function of a group of variables. The first one is the difference between family income, and that's how they write it, family income, minus how much this woman is earning per hour. Okay, so, and then they divide this one by per thousand, so it's per thousand units. So they take family income, subtract from it the earning of this female per hour. Okay, not per hour, the total income, I mean, like wage, and you multiply it times the hours, so it's going to be like the whole income divided by 1000. The next variable is education, years of education, years of actual experience in the labor market. It's quadratic, experience squared, age, the number of kids, right? Less than 6. That's how it's written in your textbook. Kids LT6, less than 6. And then kids, okay, greater than 6. So this variable is the number of kids less than 6 years of age and the number of kids greater than 6 but less than 18. So the number of kids this female have from 6 to 18 years of age. Okay, and again, before you start anything, you start thinking about the signs that you would expect. Okay, hypothesize the relationship between these regressors and the dependent variable. So for the first one, it makes sense that if the female income, right, exceeds the family income, right, then you will have a less participation. Okay. In other words, if family income, I'm sorry, let me tell you in another way. If family income minus the female income increases, if this number is positive, then I have less participation. Okay. In other words, if I'm married and my husband is earning a certain income that exceeds my income, then that makes sense that I will have less participation in the labor force. I have kind of another support. So this is like how it, so you expect kind of a negative relationship. Okay. For education, of course, the more education you would expect more participation. You would expect experience to mean more participation. It's quadratic, so we did that before. So experience has a positive impact on participation, but at a decreasing rate. So this one is negative. So experience increases at a decreasing rate. Okay, for each additional unit of experience, or for each year of experience, labor participation rate of female increases at a decreasing rate. So that's what I meant to say. Age might be the case as the person gets older, less participation. Number of kids, this is what we want to test, but it makes sense that if a female has kids or less than 6, and as this number of kids who are less than 6 increases, then most likely labor force participation rate decreases. Okay, and then between 6 and 18, we will find out. We would expect it's gonna fall, but we would kind of compare this coefficient with this coefficient and see, does it really matter if the age is less than 6 versus age between 6 and 18? I think it matters because this age the child start to go to school. So the impact on labor participation is going to be less than here. Okay, might not be significant, so we will see. Okay, so I want you to see this example from your textbook, page 593. You have actually 3 columns: the LPM, the probit, and the logits. Okay, Or you know what, I actually can, let me take a picture of this example just to make your life easy, or actually my life easy. So let me try to take a picture. Okay, so this is the example. I'm trying to get it all. So okay, so let's use this photo. Okay, done. All right, so this is what I want. I think this is much easier than referring to the textbook, so you just have it right here. So let's see. As I was telling you, you have LPM, which is simply OLS. You have logit, which is computed by maximum likelihood estimation. You have probit, computed by maximum likelihood estimation. Again, referring to Alex, let me just maximize this one. Referring to Alex's question in class, he was asking me about the signs. So whatever sign you get here, you should expect to get the same sign, right? So the logit and the probit model would give you signs that would tell you something about the direction of the relationship, positive, negative, and so on, okay? To, let's say, analyze the impact of, let's say, one of these variable age. Let's try education, for example. What is the impact of 1 year increase in education? We expect, using the LPM, which is simply OLS, that for each additional unit of education, or for each additional year of education, holding all other variables constant, the participation of females increases by 3.8%. This is according to LPM. It's statistically significant. If you divide these two, you will get it statistically significant, right? What about the impact of education in the logit model? I can see it's positive, right? So this variable is positive. I can see it's in the probit is positive, right? I cannot say anything about this number or this number. I'm just looking at them. In order to be able to analyze the impact of education, then I have to plug all of these coefficients inside. Oh, so this is the logit. Inside I have to plug all of these coefficients inside the logistic function, right? And let's say f of z, and it's going to be 1 over 1 plus e to the power minus z. And what is z? Z is just simply all of these coefficients and multiply times the x's are z. Okay? So, and the same thing for the probit. If I want to analyze the impact of a 1 unit increase in education, then I have to take all of these x's into the logistic distribution function. So let's say, for example, I'm going to have this number as the intercept, plus I'm going to have this one, which is negative 0.12 times 0.12 times the variable, which is the wife income, as the wife income increases, right? Or the family minus wife income increases, the participation rate falls. If the family income is high, so there is no reason for the women to go to work. That's based on the sample estimated here. And then you're going to have plus 0.131 times the variable education plus 0.123 times the variable experience plus, also this is negative, 0.0019 times experience squared, and you keep going, right, until the very last one, which is plus 0.036 kids greater than age 6, and you close the bracket. But then I have to give you some values for these, right? So I have to give you, let's say all the variables are analyzed at the mean, and then I'm gonna choose one of them to say it's greater than the mean by, let's say, 3 times. As you have, let's say in the example of your of the last year final, it was what's the impact of the increase by 3 times from the mean. So you get the mean and you multiply it times 3. So in the textbook, I want you to stress on this part, okay? So the biggest difference between LPM and logit probit is that LPM assumes constant marginal effects of education, kids 6, and so on, everything. And when I say marginal effects, it's like the betas, right? The beta of education, the beta of kids is just constant. We didn't put it inside a function or anything. The logit and the probit imply diminishing magnitudes of partial effects. So if I'm analyzing in the linear probability model, what's going to happen to labor force participation if female has one additional child? One additional child, so you go back here to a small child, so we're talking about this variable here. One additional child, we're using the LPM, will reduce the probability, right, of joining the labor force, right, by about this value, okay? So, and then just notice that regardless of the value of the other, or the levels of the other explanatory variables, or you can say holding them constant. If I'm trying to estimate this marginal effect from the probability model, then I have to give you some values. So the values given in your textbook, again, are the means, sample averages. So they're giving you like the sample averages that you need to plug, and you want to see what's the impact of the decrease in the probability of working if I have 0 small child versus 1. So what you're going to do is you take your CDF, you have it like this one. One time you're going to plug for the variable which is called kid less than 6, right? Isn't it? It's called kids less LT, less less L and T6. So the variable which is called LT6, and this one is going to be 1 time equal to 0, and so 1 time is going to be equal to 0, and 1 time is equal to 1, and you take the difference in probability. So if the female has no small children, the probability of participation is 0.707. If she has only one child, then it's 0.373, right? So that means there is a fall in the probability of participation by 0.334, okay? And okay, so that means the probability falls, right, when a woman has one young child. You can actually repeat the same thing. What is going to happen if I have 1 to 2? So we first started from no small children to 1. And then what's going to happen if I have 1 to 2? So you're going to have the CDF for beta naught plus beta 1. You keep going for all the variables. But for kids less than 6, one time I'm going to have it equal to 2, and then I'm going to have another one with all the parameters, right? Beta naught plus, let's say beta 1, just trying to be neat. So beta naught plus beta 1, and then you add all the parameters, and then the parameter, let's say, of kids less than 6, and keep going. So one time I have it 2, and the other time I'm going to plug here 1. It makes sense that if the female has already one child, right, then the probability of reducing her participation in the labor market doesn't matter much if she has 2 kids, right, from 1 to 2. So the fall here is 0.33, 4, and here is the fall is 25.6. Okay, so again, so if you want to compare this with the linear probability model, you need to make sure that, you need to make sure that, okay, so we need to make sure that, let's say, if this is, if this is 1 unit increase in this variable, from 0 to 1, or from 1 to 2, or from 2 to 3, it's constant, right? But if I'm using the probit model as I just did in this example, every time we're plugging it into the CDF, we keep getting a different impact on the labor force participation. So that means it's kind of nonlinear. It's basically nonlinear. And the same thing if you try the logit, it's nonlinear. Okay, so the impact here is going to be all the time a fall of 0.262, right? If from here to here, 0.62, from here to here, 262, and the same thing 0.262, but it's not the case if I'm talking about logit or probit. Okay, all right, so here again, I just want you to read this part, and it's about education. What's going to happen how education affects the labor force participation rate. And they do have a graph here, which is just graphing 2 variables, the y and education, one of the axes, years of education, one of the axes, and they have it, they're both on this graph. And as you can see, the straight line one is the LPM, so this is LPM, and this one is the probit model. And as I said in class, it's usually when we draw this probit between 0 and 1, we usually say it takes like an S shape, right? So in practice, doesn't have to be that exact S shape, like the nice S shape, but it has some curvature. As you can see, like when you compare it to this straight line, this one has some curvature here, and it's going up. So it's kind of a smooth S. Okay, but it basically would tell you that the change from, let's say, 4 to 8 would have a certain impact if I'm talking about a linear probability model. But if I'm talking about the probit model, the impact is less. If I increase from 8 to 12, okay, then this is supposed to be the same impact on the constant or the linear probability model. But it won't be the same for the probit model. And then you keep going, you will find that this one is the slope is still constant every time I'm talking about the linear probability model, but it's not the case for the probit model. Okay, so in order to understand these types of models, you really need to practice. So you really need to practice. So I want you to do last year's first question, and I'm going to post for you a non-graded quiz on the probit and logit models. All right. Okay, so I'll see you on Wednesday. Okay, so Tuesday class is canceled, as I said, so I'll see you on Wednesday, and I'm going to send you a reminder. All right.